Lucas Dimoveo, and he is from the Community College of Denver in pre-engineering. He plans to continue education at CU in applied mathematics.
Good morning, everyone. My name is Lucas Dimoveo. I worked with Stefan Tulich at NOAA, and we looked at the Nino 3.4 region. There's going to be a lot of jargon, so I'm going to try to define everything before we get going. All right, next slide, please. So the ENSO cycle is basically our description of El Nino, La Nina, and neutral, which is basically what happens in between El Nino and La Nina. El Nino is corresponded with high sea surface temperatures, SST. La Nina is generally low, and neutral is kind of within the mean if we're thinking about some normal distribution, even though it gets a little more funky. So I'm sure you've all heard of what El Nino and La Nina does in the continental US, everything from drought to hurricanes, tornadoes, all of the really crazy stuff that we associate with ENSO years. But there's also mundane things like rainfall patterns and behavior of the jet stream. That's a little bit outside of the scope of this talk, but I just wanted to give you a sense of why this stuff is important. Okay, next slide, please. So SST, sea surface temperatures. OLR is outgoing long-wave radiation. So there's kind of infrared radiation coming off of the surface of the Pacific Ocean, and that's measured by a NOAA satellite. So that's where we got our time series data, and that's in watts per meter square. FFT is the fast Fourier transform. There's a lot of cool tutorials online, but it's basically taking our physical data and turning it into Fourier space, which is basically like the sort of graph that you would see when working with audio. How there's power and there's hertz and that kind of stuff. DJF are the 90 days from December 1st to March 1st. And the power spectrum is basically the absolute value of our fast Fourier transform output. Okay, next. Okay, so the methods of this project, it was a lot of working with multidimensional date time arrays, which was a lot of fun. We looked at a patch of the Pacific Ocean called Nino 3.4, and that's in the east central region of the Pacific Ocean. And let's see. Oh, so the reason why we didn't analyze the whole time series data is because during the summer months, ENSO activity tends to shift a little bit north outside of our rectangle. Just kind of like an intuitive sense, seasons carry variation with it. And so we wanted to remove seasonal variation to kind of focus in on anomalous data. So we basically took these 90-day chunks of winter for every year from 1978 to 2020. Next slide, please. And we plotted the distribution and just tried to figure out like where El Nino and La Nina years lie on our graph. So there's a few interesting things going on. First, for the top graph, our orange line is the mean, which is about negative 5.8 watts per meter square. The green line is negative 31.8, oh no, it's here, negative 31.4 watts per meter square. And our red line is positive. Now, basically what's going on is with our El Nino year, we have a negative OLR value because there's convection and cloud cover preventing our satellite from getting that data. So it's inverse from the sea surface temperatures, if that makes sense. So what that means is below our green line, we have some pretty prominent El Nino years, but nothing really quite touches or exceeds our red line. And that's because if you look at the graph right below that, our data doesn't have a normal distribution, which means that we can't apply like -1 standard deviation and a positive standard deviation under that kind of bell curve, if you can imagine it. There's some statistical techniques to analyze this. I did not know them. So, and so that's why it was outside of the scope of the project. And so that's why we didn't get something more precise. But basically what we did was we took these 42 dots, which represent 90-day chunks for this 42 years. And we plotted the, excuse me, the mean power spectrum. So we got it into Fourier space, and then we just took the absolute value to see what frequencies and cycles per day have the most power. Okay, next slide, please. Okay, so we took 1999, which was one of those dots that approached our red line and called it a La Nina year. Of course, if we're going just by the methods, then it would be kind of difficult to determine if it actually was a La Nina year. But that's one of the points that we took. And then we also took 2015, which was a particularly strong El Nino year. And so 2015 is represented by the blue stick graph, and La Nina is represented by the green. So just by looking at this, it's kind of like there are obvious differences in the graph, but I ran out of time with the project to really find the answer to how ENSO cycles affect kind of daily OLR values. I forgot to say that at the beginning of the talk. So we basically wanted to answer how these large ENSO cycles vary on the day time scales for OLR values. So that's the meaning behind all of this computation. Sorry about that. Next slide, please. Okay, so we've done all of this computational work to kind of remove all of the normal parts of our data. And the next step would have been to find the mean for every day within our time series. So we basically, we have our arrays, and we're going to pluck a date from our array and create, let's just say November 15th. So we'll create 42 values of November 15th. We'll find the mean, we'll find its distribution, and then we can actually say during some point in the ENSO cycle, this is how far our OLR value is away from the mean for that day. So that would have been the answer. Didn't quite get there. Turns out working with date time, multi-dimensional arrays is rough, but it's the meat and bones of a lot of these computational techniques. So next slide, please. So I'd like to acknowledge my funding source from the NSF, Cyrus and Rex. Rex, you guys have been awesome. I love all of you. And next slide, please. Yeah, like my mentor, and just Mark Piper, which like he didn't have to answer all of my weird Python questions, but he did. Beck for just giving me all of the encouragement and practical career advice. Alicia for giving me pep talks when I thought I couldn't do it. So yeah, and Donna, everyone, I love you guys. So thank you.
All right, great. Thank you so much, Lucas. That was excellent. So we have a couple of questions here for you. Filters might be used to clean up the air. Oops, sorry. Wrong. Okay. What did you find most surprising in this project?
Yeah, I think the most surprising part was working with date time. It was surprisingly difficult, especially turning something like Julian days into Gregorian dates, which is basically like, so there are two different calendars. Astronomers use one, and then the Gregorian date is what we're using. And so there's not a lot of like Python support for this kind of thing. And so after I'm going to try to go back and like complete the code, but I want to like contribute to that because there's not a lot of support in like academic software engineering for this kind of stuff. So.
All right. And one more question. It's really cool that you noticed the hopefully I'm pronouncing this right, the non-Gaussian distribution of your data. Do you think people often apply normal statistics to this data?
That's a really good question. I don't imagine people would do it at the level of like academic research, but I mean, maybe that, like, I think because most introduction to statistics uses kind of normal distribution as examples, I think people might assume that you can just say like, oh, I'm going to find the mean and the standard deviation and the variance, and it's going to be the same for every data set. And that's not the case. It's definitely a mistake that I made until I plotted out the histogram, and I was like, wait a minute, this isn't quite right. So yeah, I'm looking forward to learning more data science and statistics, how to handle data sets like this.
All right. Great. Thank you so much. Okay, we're going to go ahead and move on to our next presenter.